The Lorentz velocity transformation equations. Now suppose that an object has a velocity component ux prime measured in the s prime reference frame. So how do we report ux prime? It is dx prime dt prime, derivative of its position with respect to time. Now we have these difference equations. Delta x prime is gamma delta x minus v delta t. If we write this in differential form, we would obtain dx prime is gamma dx minus v dt. And if we write the time equation in differential form, dt prime is gamma dt minus v over c squared dx. So if we take this derivative dx prime dt prime, we will have gamma factors cancelling. So we're dividing these, dx minus v dt divided by dt minus v over c squared dx. So if we take this into dt parentheses, we obtain dx dt minus v. If we take this into dt parentheses, we obtain 1 minus v over c squared dx dt. Alright, so this is dx dt. Now, what is dx dt? That is the velocity component measured in the s reference frame. So this would be ux. So this would be ux minus v divided by 1 minus ux v over c squared. So we have obtained the velocity transformation. And what was the case for the Galilean transformation? If we look at the Galilean transformation here, we would have dx is equal to dx prime plus v dt prime. So if we have t equals t prime, this would become dx is equal to x prime dx prime plus v dt prime. So dx prime dt or dx prime dt prime would become ux minus v. So that's the Galilean version, ux minus v. So when v is much less than c, we obtain 1 here in the denominator because this will be negligible. So Galilean transformation will be recovered. And if the object has velocity components in y and z as well, let's think about how to transform those. Now we have y prime is equal to y, so the delta y is equal to delta y prime. So dy prime is equal to dy. So we take dy prime dt prime. It's dy divided by gamma dt minus v dx over c squared. Again, taking this into the derivative of with respect to time. So taking it into dt parentheses, I obtain dy dt gamma dt 1 minus v dx dt over c squared. So this becomes the velocity y component measured in the s reference frame uy divided by gamma 1 minus uxv over c squared. And the story is the same for z. So uz prime would be uz over gamma 1 minus uxv over c squared. Alright, so when v is much less than c, gamma is going to become 1, uxv over c squared is going to become 0. And if ux prime is equal to c, so if it's the light that we're observing in the s prime reference frame, then using the transformation from s prime to s reference frame, we would have to make this a plus here, and so we would have to change the primes. So this would be unprimed, this would be primed, and we would have, instead of ux minus ux prime plus v, so that would become c plus v, and then 1 minus uxv over c squared will become 1 plus cv over c squared. You can see that this is c plus v over c plus v over c, which is c. So the speed of light measured in both reference frames is the same, which is consistent with Einstein's second postulate of constancy of the speed of light. Okay, so s prime to s reference frame, as I said, we just change the primes and make the minus signs plus in order to obtain the transformation equation. Let's take a look at an example. Relative velocity of two spacecraft. Two spacecraft A and B are moving in opposite directions as shown in the figure. An observer on the Earth, S reference frame attached to the Earth, measures the speed of spacecraft A to be 0.75 c and speed of spacecraft B to be minus 0.85 c. Find the velocity of spacecraft B as observed by the crew on spacecraft A. So A becomes my S prime reference frame, so that is the relative speed is 0.75 c with respect to the S reference frame. So velocity of A that is measured by the S reference frame, which I call V, is 0.75 c. So the velocity measured in the S reference frame for spacecraft B is minus 0.85 c, that's the X component. So what would be the X component reported by S prime frame, which is now the spacecraft A? So using the Lorenz velocity transformation, I have Ux minus V divided by 1 minus UXV over c squared. So this would become the velocity measured by the S reference frame minus 0.85 c minus the relative velocity of A with respect to S reference frame 0.75 c divided by 1. Ux is minus 0.875 c, so this will become plus 0.75 times 0.85, because we have Ux is equal to minus 0.85 c, V is equal to 0.75 c, c squares will cancel. And this will give us for the velocity X component measured by the spacecraft A to be minus 0.977 c. All right. So you can see that normally if you use Galilean transformation, this spacecraft would measure 0.85 plus 0.75, 1.6 c. But using Lorentz transformation, we see that it's actually minus 0.977 c, which is close to the speed of light. Now, what happens if the two spacecrafts pass each other? This doesn't change the sign of the velocities, therefore the answer does not change. So doing so, this doesn't change the sign of velocities if they pass each other, so the answer does not change. Okay, let's look at another example. Relativistic leaders of the pack. Two motorcycle pack leaders named David and Emily are racing at relativistic speeds along perpendicular paths as shown in the figure. David is moving at 0.75 c to the right, Emily is moving at 0.9 c down in the downward direction with respect to this police officer at rest in the S reference frame. How fast does Emily recede as seen by David over his right shoulder? So since David is reporting, David is the S prime reference frame that is moving with respect to the police officer at rest, S reference frame, 0.75 c. So we can use the Lorentzian transformation, velocity transformation, so we can obtain for the speed that is reported by the S observer, X component. The police observer says Emily does not have an X component of velocity, so Ux is 0 in the S reference frame. but there's a y component which is minus 0.9 c. Now using the Lorentz velocity transformation, ux prime is equal to ux minus v divided by 1 minus uxv over c squared, and this will give us, because ux is equal to 0 here, you can see this is 0, this is 0, minus v, which is minus 0.75 c. On the other hand, for the y component, uy prime, we have uy divided by gamma times, there was also a gamma here in the Lorentz velocity transformation. I think so. If we go back, no, there is no gamma there. All right, so this was correct. So there is a gamma for the y transformation, 1 minus uxv over c squared. So that's going to become uy stays. We have ux is equal to 0, so this is going to be 0 uy over gamma, which will become 1 minus v square over c square square root, that's 1 over gamma, multiplied by uy. So if I substitute 1 minus 0.75 square root multiplied by minus 0.9 c, I will obtain uy prime to be minus 0.6 c. Now what is the speed measured by David over his right shoulder? Well, it's going to be u prime, which is square root of ux prime plus uy prime, x prime square plus uy prime square root. So this will be square root of 0.75 square plus 0.6 square times c. So we will obtain for u prime 0.96 c. All right. Okay, so we have talked about Lorentz velocity transformation equations. In order to obtain these equations, you have to look at the Lorentz transformation equations in difference form. So delta x prime is gamma delta x minus v delta t prime is gamma delta t minus v over c squared delta x. So dx prime dt prime, which is ux prime, is dx prime over dt prime. So for dx prime, you substitute gamma times dx minus v dt, this for this one, and for dt prime, we substitute gamma times dt minus v over c squared dx. Gammas cancel, so we obtain, if we take it into dx dt parentheses, ux minus v over 1 minus uxv over c squared. For the Galilean case, v is much less than c, we have ux minus v. And for the y component, we do the same. dy prime is equal to dy, so that doesn't change, but dt prime is again gamma dt minus v over c squared dx. So if you take it into dt parentheses, we obtain the corresponding transformation equation, uy divided by gamma 1 minus uxv over c squared, and similarly for the z component. And we see that if one of the measures the speed of light c here, so for ux prime is equal to c, if we substitute here, ux will be, so for the transformation to the x reference frame, it will become ux prime plus v over 1 plus ux prime v over c squared. So ux prime is c plus v, 1 plus c v over c squared, and this will become c in both reference frames, which is consistent with Einstein's second postulate. And we looked at an example where a spacecraft A is moving with a relative speed 0.75 c on the x-axis with respect to the Earth reference frame. So this sets up our S prime reference frame, and we're trying to report the speed of B as observed by A. Galilean transformation says it should be 1.6 c, which is not possible because we cannot exceed the speed of light. So using Lorentz transformation, ux prime is equal to ux minus v over 1 minus ux v over c squared. Ux is minus 0.85 c as measured by the Earth reference frame. V is plus 0.75 c. And this gives us minus 0.977 c instead of 1.6 c. If they pass each other, the sign of the velocities don't change, so the answer does not change. And then we looked at another example where a police officer is watching David on a motorcycle moving at 0.75 c to the right, and David is observing Emily, so this is going to give us the S prime reference frame. Emily, with respect to the officer, is moving at minus 0.9 c in the minus j hat direction. So ux measured by the officer for Emily is 0, and uy measured is minus 0.9 c. Then we do our Lorentzian transformation, ux minus v, where ux is 0, so we obtain minus v, which is minus 0.75 c. So David thinks the x component of Emily's velocity is minus 0.75 c. And for uy prime, uy over gamma times 1 minus uxv over c squared, ux is 0. We obtain uy over gamma, or uy times square root of 1 minus v squared over c squared, which gives us minus 0.6 c. And therefore the speed observed is square root of ux prime square plus uy prime square. That's 0.96 c.